Hello everyone, welcome to our Alternative Building Methods webinar. We've got a couple of really great speakers for you tonight, Lance Kairl from House of Bales and Stephen Dobson from Ramtec. My name is Kathy Witter. I am the coordinator at Gawler Environment Centre. We are a local community group and we put on a lot of different workshops and webinars and events to engage our community about environmental protection and sustainable living. And we've got a bit of a webinar series happening at the moment, of which this is the second one. And I would like to firstly acknowledge that tonight I'm on the traditional land of the Kaurna people and would like to acknowledge my respect for their spiritual relationship with their country. I also acknowledge the Kaurna people as the traditional custodians of the Adelaide region and that their cultural heritage beliefs are still as important to the living Kaurna people today. And obviously we have people tuning in from all kinds of different country, and I'd like to acknowledge the custodians of those regions too. So without further ado, I'll hand over to our first speaker, who is Lance Kairl from the House of Bales. So Lance is SA's most experienced and respected straw bale builder. He's a licensed builder and building works supervisor and started House of Bales in 1997. He's worked with owners and builders to facilitate construction of straw bale buildings. He is passionate about refining and developing more efficient and cost-effective ways of creating long-lasting, well-built straw bale projects. Over to you, Lance.
Thank you, Kathy, and thank you very much for the Resource Centre for holding these talks and for inviting me to be involved. I'm here to talk about straw bale construction, and the other speaker will be talking about rammed earth. Straw bale construction is primarily insulation-based building materials, and rammed earth is primarily thermal mass-based building materials. So I'm sure he'll have more to talk about that side of it, but I'll talk about the insulation side and how straw bale fits in with that. But firstly, a little bit on how we construct straw bale buildings. The picture you see is a straw bale building under construction. We primarily use a post and beam structure, and that is there's posts that hold up the roof, and we build the bale wall in between the post as they go around the building. The post dimensions can vary from square 90 by 90 posts through to wider full width manufactured buck, if you like, or wider post sections that are the full width of the bale wall. We stack bales in between the posts and then tie them down and compress the bales in situ. The compression is not dramatic, but it is enough to give that stack of bales some integrity. The bit like when you move house, you grab 20 books from the bookshelf, you squeeze those books a little bit, and that holds that row of 20 books in one unison block. You let go of the pressure and it all falls apart. So it's that little bit of pressure that gives it some rigidity and takes it away from being that loose stack of bales, which I often call liquid. Quite a liquid form until they're compressed down. We also have fixed cross bracing within those structures. The compressing of the bales and the placing of the bales, if you put them in with a bit of pressure, can start to deform those columns and posts out of shape a little bit, which is pretty critical when it comes to doors and windows, that you keep those spaces fairly vertical so that the windows and doors fit easily. Straw bale construction is often done in two methods. The picture in front of you shows the bale on flat, so the strings on the bale end up in the middle of the wall. Bale on edge would actually be the strings being exposed on the inside and the outside of the wall. The R values for both orientations is pretty much the same, and that's to do with the energy flow of heat through the stalks of the bale and the orientation of those stalks. So whether it's on flat or on edge, the R value is around the R8 to 10. The variation depends a little bit on construction methodologies and attention to detail, but R8 is well accepted as being the low end of a straw bale R value, and R10 the high end. The radically high numbers of 48 and 56 are imperial based measurements and calculations for R values, whereas we use the metric based. Post and beam systems up, bale walls in place, tied down. Wire netting is used by us in critical locations, so external corners and possibly around door and window shapes, to give some assistance there in reinforcing the render and holding the shape. Wire netting is not needed for the render to stick. The render sticks very well to the straw. So in this case, you can see what is spray rendering, and it's first coat render being sprayed onto the straw. And we do a three coat system, 2 coats of about 16 millimeters, and then a final coat of about 3 millimeters. The first coat gives us an even key. Second coat will give us shapes and build up to towards our final thickness requirements. And then final coat is really just even colour and texture. Render finishes vary quite a bit, from quite smooth, even, as the photo here is, quite rounded corner externally there. And as you can see along the face of the wall, it's quite vertical and quite flat. This is the sort of work we do. I guess some of our early work was a bit more undulating and organic, but certainly a nicer, neater finish for the type and quality of homes that we build. Variations on the theme. So this is what we would call a bale house wrap. This is a transportable house, of which we've extended the footing or floor space, if you like, on the outside of the building, and then installed straw bale walls, new windows, extended the roof, and put rendered straw bale walls to the outside to increase the thermal performance of the house, the insulation. This is, of course, in this case, with a transportable, we've insulated the underfloor and radically increased the insulation in the roof. Other mediums that we've used, and this particular straw bale is fairly traditional straw bale to the front, the yellowish sandstone coloured render to the front of that house. The corrugated iron sections to the rear are also straw bale walls, where we've, at the request of the architect and the owner, wanted a different medium, a different finish. And so we've used a system commonly referred to as rain screening within the straw bale building industry to protect the bale walls from that wind-driven rain, and also to allow for the bales to still breathe and to perform properly within that situation. So there's a variety of things that we can do to do that. And I think that's probably the basics of it. We build straw bale homes all over South Australia and occasionally interstate, and work ourselves professionally as builders, so we can completely build your home, or we work as subcontractors to other builders, which we do interstate quite often, and also work a lot with owner builders, whether that be a little bit of assistance from us on technical stuff and the occasional on-site assistance, or through to the other way around where effectively we build the house, but the owners are on site helping wherever they can, whenever they can. Thank you very much for the opportunity to speak to you, and I trust it's been informative. Thanks very much, Kathy, for inviting me.
Okay, if anyone has any questions for Lance, please type them into the chat room and I'll read them out for him. Apologies for the technical issues that we're having. Naturally, none of this happened when we did our test run the other night. Everything, sound and visual, was fantastic, but yes, it's all very unpredictable.
We just both happen to be speaking to you from rammed earth buildings tonight. So I happen to be in a rental property that is rammed earth walls, off-grid, standalone power, as I have been for the last 20 odd years. So it's been nice to find a rental property that affords me the opportunity to still be not having to pay for an electricity bill.
Marvellous. Now, I've got a question for you from Matthew, who has a query regarding bushfire areas and special treatment required in high bushfire zones.
Hi, Matthew. Great question. Straw bale construction has been tested and is certified for all bushfire areas up to and including Bale flame zone, BALFZ. Predominantly 35 millimetres of render cover will achieve that. In order to actually get that through your council, you will need to provide the documentation, and that is available through AusBale, the Australian Straw Bale Building Association's website. There is a fee for that, and it is only available to members. So you will have to pay the smaller fee to become a member, and then you can download that documentation and add that to your documents that you submit to council.
Oh, great. Now I have another question from Cindy, who says, hi there, this isn't specific to straw bale, but do you think you could use render with a wire matrix to cover a pan trailer / semi-trailer for a tiny house build?
Yes, certainly rendering to other substrates is possible. And yes, a mesh matrix would probably be required to help it stick as well as to reinforce it. Difficulty, I would think, would be the weight involved and how that will bend and flex a Pantech trailer. As with a shipping container, shipping containers are probably more rigid, but that additional weight, we're talking significant weight in the thickness of 35 mils of render. And so that would need to take into consideration footing and I guess stability of walling systems, whatever they are.
Okay, and we have a question from Susan, who would like to know, can stucco or concrete on the outside prevent the bales from breathing and cause bales to mould?
Yes, correct in your thinking there that we prefer breathable render types. So earth is the most breathable. Lime renders are the next most breathable. Cement-based renders are predominantly, and stucco is just a form of cement-based renders, predominantly less breathable. And what we mean by breathability is something a bit like the human skin. When you get in the bathtub, you don't fill up with water, but on a hot day, you will transpire moisture out through your skin cells, and that allows your skin to breathe effectively. And that's sort of cladding we need for a straw bale building, is to keep that moisture content to be able to move out, and on some occasions into the building when there's a difference in relative humidities that allows that. The render skins, whether they are earth or lime will still keep the water out. The free-flowing moisture, commonly called rain, is kept out by the render skin, but the humidity can vary.
Okay, does anyone else have any other questions for Lance? No one's madly typing at the moment, so perhaps we'll move on to our next speaker, who is Stephen Dobson from Ramtec. So Stephen is one of Australia's consummate exponents of rammed earth and is managing director of Ramtec, which was established in 1979. And Ramtec has built over 750 rammed earth structures over 40 plus years. Now, Stephen is a founding member and life member of the Earth Building Association of Australia, and he is passionate about passive low energy architecture, low carbon building and producing buildings utilising thermal mass, which when well designed and operated are safe and importantly avoid the need for significant energy for heating and cooling. Now I'll just unmute Stephen.
I'd just like to start probably with a definition of rammed earth, then a bit of history, old and new, then talk about a few measurement concepts for green, sustainable building, energy measuring systems, etc. Talk about how rammed earth meets them and how rammed earth works well. So a definition of rammed earth, it's a material placed in a formwork system and compacted down in layers. It's built in situ. Normally, it can use material from on the site, but it doesn't have to. It can use imported material or material on site or a blend, depending on what's available where. It can be made off-site and transported around, but that is not generally done in Australia. But it certainly is in Europe, where they make them all winter in a big factory and then install them over their shorter summer. Rammed earth goes back a long time in history. The oldest building I've seen is about 10,000 years old in Turkey. All through the biblical areas, rammed earth is a very common form of building. And particularly in the hotter countries where rammed earth, if it's well designed and operated, can give you thermal comfort without the need of air conditioning. Given that air conditioning was only invented in 1902, prior to that, high thermal mass, which is what rammed earth is one of its properties, can give thermal comfort. And the technique is to, in summer, when it's very hot during the day, to open the building up at night, cool that thermal mass down, store that energy. Then when the heat of the day comes, to close the building up a bit, draw the curtains up a bit so that that coolness is stored in the building and is radiated to the occupants. And now you're using radiation as a cooling technique, which is far more efficient than blasting cold air on your face. Humans like it better. It works. It's a more efficient way of cooling. Conversely, in winter, when outside conditions are cold, the sun angle must be designed right so that winter sun can penetrate the building, fall on hopefully a massive floor, such as a concrete floor. You can make rammed earth floors. Falls on the rammed earth walls, stores that warmth when the sun is shining and carries it through. Then it's carrying it through the night or the cold parts. And again, you're getting radiation warming. So it's a very low-tech way of doing it. It's been done for thousands of years, and it is being used ongoing, and its popularity is increasing. The number of existing rammed earth houses around the world is hard to say, but between a third and a half of the world's population of 7 billion people live in earth houses, and mud brick and rammed earth are the predominant building types. In China, there are 100 million people living in rammed earth houses alone, including in some very hot areas and some very cold areas. And a couple of years ago, the world's best architectural house was a small rammed earth house built in a very cold area of China, hugely successful. There's currently a house being monitored, a rammed earth house in northern Canada, in Alaska. I've forgotten the name of the town, but it's performing very well. And also they're monitoring a lightweight, well-insulated house, and the thermal mass house is by all their measurements outperforming, which is pleasing. So getting back to a hot climate, in Australia, we've got 8 climate zones from desert, number 1, to alpine, number 8. Rammed earth's been used in all of those climate zones, and particularly it's used in climate zones 5 and 6, which is Adelaide and Perth, and where most of the people live in Australia. An experiment we did in Kalgoorlie, which is a very hot desert climate, we built 2 rammed earth houses alongside a lightweight house. None of them had air conditioning, all were monitored. All had ceiling fans. When the outside temperature reached 35 degrees Celsius, the lightweight house occupants said it was uninhabitable and installed air conditioning. At 45 degrees Celsius, the rammed earth house occupants said they were still comfortable and things were okay. So and that's in a scientific paper put out by the University of Western Australia. It's in the public domain. Anyone can read it, and pretty impressive. But for climate zones 5 and 6, most of South Australia and where the people live, you can, if you design your rammed earth house right and operate it right, and operate it just means opening and closing doors and windows in response to outside conditions and in anticipation of outside conditions, you should be able to get a house that needs very little or no air conditioning. That's quite easy. And if it's very well designed with passive low energy architecture, you can have a house that doesn't need much heating. And this was exemplified by the the mud brick buildings around Adelaide. Chris Howe was a mud brick maker at Springfield near Adelaide for many years. He had the cheapest houses in Australia as certified by Cordell's costing building magazine, and high thermal mass, very successful. In Melbourne, mud brick houses, hugely successful all around there. And in Western Australia now, rammed earth is extremely popular. In Margaret River, a few years ago, 25% of all new houses were made out of rammed earth, largely because there were very suitable materials there. People wanted an eco house or an escape. They were a lot of holiday houses. And so very successful. Just on the structural properties of rammed earth, it has been built to in excess of 40 megapascals, which is a very high strength. You could build about a 20-story building with that. There are 6-story buildings in Shabam in Yemen, in a desert climate, which are hundreds of years old. And in using rammed earth without cement, the strength is typically 2.5 or 3 megapascals, which in Europe has been used to build 4-story buildings. Ramtec has been involved in a 4-story building, Kairl Valley Hotel in Brisbane, an enormous building. It's quite old now. It was $25 million when it was built, the hotel, and the rammed earth walls are about 800,000. The biggest rammed earth project in Australia right now is a building at number 1 Great Ocean Road in Torquay in Victoria. near the opposite side of the bay to Melbourne. It's a 4-story building, $100 million hotel, $5 million worth of rammed earth, load bearing, enormously successful. So I need to talk about some of the ecological and green properties, and I'll try and talk about some of the measurement systems. So there are measurement concepts, and I guess sustainability, I would call that as the basic objectives of sustainability are to reduce consumption of non-renewable resources, to minimise waste, and to create healthy, productive environments. Now, rammed earth ticks all these boxes. One of the lesser known benefits is the biophilic properties. So I might just launch into them just because they're not too well known. So biophilic design is an approach to architecture that seeks to connect building occupants more closely to nature. And it incorporates things like natural materials, like earth, natural lighting, good design, natural ventilation, that's very important, cross ventilation, things like that, a close connection to nature, and lessening the gap between indoor and outdoor living, which can be done with thermal mass quite easily and very effectively, and involving natural landscape features and natural elements to create a more productive and healthy environment for people. So it's been found that, or just probably a shorter definition would be that biophilia is defined as the inherent human inclination to affiliate with nature. And this is done very well with rammed earth, from the appearance, from the thermal mass, from the using local materials, from the recyclability, from the lack of outside energy sources needed for thermal comfort, etc., etc. And it's been found that with good biophilic design, it has actually measurably helped office workers to be more productive. It's encouraged children to learn in schools. There are many rammed earth schools around Australia, very successful, and providing a healthier building and helping hospital patients get better. A few rammed earth hospitals have been built in Australia and overseas, and that natural environment really does help. If I could talk about some of the measuring techniques, there's Green Star, there's Eco Specifier, there's LEED, LEED, there's BREEAM, BREAM, Green Building Council International, Green Building Council of Australia. There are all these green measurement techniques. Some of them just exist to give their proponents a good feeling. There's NatHERS in Australia, the National Home Energy Rating System, which is the STAR system, 6 stars. This only measures energy used in a computer program designed to model the amount of heating and cooling that's needed, and it's then set against the allowed heating and cooling in the various climate zones within Australia. It's postcode dependent, and then you get enough stars or you don't. But there are alternative ways of doing it. In France, their building code allows 50 kilowatt hours per square metre in any house for all energy consumed, including electricity, gas, wood, the lot. But you can go up to 62 kilowatt hours per square metre maximum with on-site generation, solar, wind, etc. But that's the maximum. It overcomes what is commonly done in Australia, where a terrible house is designed from terrible materials. Then they just put a big enough solar panel on there and say, hey, it's a green building. Well, in my view, that doesn't count. You need to measure the embodied energy. And in Australia, that's not done. One of the first countries to do this will be France in a couple of years, where they will measure the embodied energy, which is quite telling. A better system is Active House, which is a European system which takes into account a whole host of things like thermal mass, like on-site generation, like acoustic environment, like lighting, like relation to the outdoors. It's quite a complicated metric. And to me, it is a much better metric than what is being pushed in Australia, which is passive house. Another good German measurement system is DGNB, which is a government system designed to get into where everyone wants to go, which is into low carbon building, to achieve thermal comfort without using a lot of energy. This is where everyone wants to go, and there's endless discussion on how to get there. And one of the, well, probably the world's most stringent green building standard is the Living Building Challenge. This is not common in Australia, but it's growing worldwide. It's probably the ultimate green building standard that can be applied to any building type around the world. And the idea is that they incorporate regenerative design solutions that actually improve the local environment rather than just reducing harm. It's interesting that the creator of the Living Building Challenge is an American, Jason McLennan, who actually lives in a rammed earth house and claims openly that it's as good as you can get. So I think that's a pretty good advertisement from an absolute world leader. From the Living Building Challenge has come the Living Product Challenge, which is a framework for manufacturers to create products that are healthy, inspirational, and give back to the environment. And they have this thing called the Declare label, which is a product transparency disclosure to identify where a product comes from, what it's made of, and where it goes at the end of its life. And so rammed earth comes from the earth, it's processed on site, it's used as a housing or a building for perhaps a couple of centuries, and then it returns to the earth. So I think that's we're headed in the right direction. I should point out that there's a lot of talk of these multi-component houses, these modern lightweight buildings, tightly sealed, well insulated, multiple layers, all sorts of skins, some of them quite thick, quite of them quite complicated, and some of them quite problematic in terms of interstitial condensation, which is condensation in the inside your wall where the dew point is lower than the wet bulb temperature of the air, resulting in mold happening inside your wall that you don't know about. It can be very toxic and it can be quite life-threatening. I would encourage anyone getting one of these houses to get a guarantee that there will be no mold over the life of the house, either within the wall system or on the face of the wall system. I mean, people often get a separate guarantee on their roof not leaking on their house just to be very sure, because that's pretty important. I would regard a mold guarantee to be pretty important on some of these other houses that are springing up. And also read the publication by the Australian Building Codes Board on interstitial condensation, and it's called Condensation in Buildings. It's a handbook, it's quite long, and it's quite scary. I'd like to get on to sort of resilience of buildings in that there are many different ways of measuring resilience, and houses should be resistant to all of these. There's coastal inundation from the sea, but particularly rainwater floods now. I mean, rammed earth has been built. I've had a house go underwater with on a few occasions, sadly, and almost no damage other than some mild staining, which could be easily removed. So the buildings they're not flood proof, but they're very resistant to floods, which is pretty important. In the Kakadu Visitor Information Centre, it's built on a floodplain, and we built rammed earth footings, and then small rammed earth walls 1.2 metres high, then a large concrete slab, then the building proper on top of that. So floodwaters can go under the building, but also we've had buildings where floodwaters have gone through the buildings unexpectedly, but we're quite successfully in that the walls structurally were quite okay. All buildings need to have resilience against heavy rainfall and wind-driven rain. Rammed earth does this very well. We've built lots of houses in cyclonic wind areas. The highest wind speed we've designed for was 330 kilometres an hour, and it required a 300 millimetre thick rammed earth wall. It was 3 stories high, and it was in the Port Hedland seafront area. Bushfires, we need to design against them, and rammed earth has the highest fire rating that you can get, which is 240, 240, 240, meaning a 4-hour rating in each of the parameters that measure fire. The bushfire code specifically says that mud brick is suitable for flame zone area, and so is rammed earth. Now, talking about global warming, the planet seems to be getting warmer, so areas that are cold are getting hot, and places that are hot are getting even hotter. So if you build with thermal mass and design it right, these places work well. You know, an example in Australia, 45 degrees Celsius and still quite comfortable to live in. The Middle East, where it gets even hotter than that, centuries of successful use, and this is without air conditioning. So if you find that your area is going to get hotter, you want a house that is going to keep you comfortable as the climate rises, or the temperatures rise with the climate. And given that your house should last a couple hundred years, and global warming should be pretty advanced in a couple of hundred years, it's good to think about the future so your house doesn't become uninhabitable 100 years from now. Another thing of resilience that's extremely important is safety from hot or cold snaps when the power fails. This has been studied quite a bit by Professor Susan Rofe of Heriot-Watt University, who's advised the Australian government and said, you guys need to take care, because lightweight, well-insulated, tightly sealed buildings, when the power goes off, people will die. And you need to think about the thermal performance of your house when the power fails, when there's a hot or a cold snap. And she did some modelling in Adelaide. There was a very near miss where she claimed thousands of people could have died, and similarly happened in Sydney, but they did not occur. But it was just that the power wasn't off for long enough when the temperatures were wrong enough. But in Europe, 80,000 people died in one of these occurrences, with few people dying in the old high ceilings, thick walls, stones, thermal mass building, and most of them dying in modern lightweight buildings. I'd like to refer to some work done by the University of Newcastle in year 2011, where they studied brick buildings at an enormous study that took years, cost millions, and their results were, one, there is no correlation between the R value of a wall and energy usage. R value is not the sole predictor of thermal performance. And they built multiple buildings and monitored them for a year. And of the buildings that they built, which were some lightweight, some thermal mass, some composite like brick veneer and so forth, they said the lightweight building was the worst performing of all seasons. So I guess I'm a thermal mass lover, and I believe that rammed earth is an excellent material. Just talking about wall thickness, you can get a lot of thermal mass in a 300 millimetre thick wall. We also build thinner walls for internal, and internal walls are important. And I would suggest, if you're planning on a straw bale house, to make your internal walls of rammed earth to get some thermal mass inside that insulated envelope would be a sensible thing. The main houses we build, however, have got rammed earth external walls and rammed earth internal walls of different thicknesses. You can insulate rammed earth walls in the centre of the wall if you want to. They are earthquake proof, cyclone proof, flood proof, bushfire proof, etc. if you take that into account. So just in closing, Ramtec does offer a design service and a build service. In Adelaide, there are at least 2 rammed earth contractors who can come and build you some walls. Ramtec have built rammed earth walls in Adelaide as well. Out at Baird Bay on the Eyre Peninsula, there's a swim with the dolphins, a little eco lodge little sustainable lodge, which we designed and built there, which you can go and stay in. But I guess I'm saying thermal mass, I think, is a really important thing, and rammed earth does it very cost effectively. It's reasonably quick to build. It's often quicker than brick. And the overall house is very long lasting, very comfortable, very desirable. And I think if we get into cost, it stands up very well. So thank you for the opportunity to speak. I'd be happy to answer any questions.
Okay, I've just unmuted Lance as well, so we can take questions for both speakers. I had one a bit earlier from Gail, who'd like to know, do the straw bales break down over time? And if so, how long does it take?
Generally, no. I think the trick is to exclude the free-flowing moisture, water, rain, and floods, as Stephen suggested. So kept in a dry state, I don't know whether I would say that they would last indefinitely, but certainly there are 100-plus-year-old straw bale homes in the United States of America that have been around for that long. So good detailing, good design, good maintenance is what's required, and it should keep your house going for long after you're gone.
Great, thanks, Lance. I've got a question here for Stephen from Matthew. Thanks for your presentation. Just a quick query regarding footings. Am I correct in assuming engineers would follow the double leaf brick requirements in AS 2870 for footing design?
Probably not. You could do that, but we have our own footing design that's better than that. It uses less concrete, it's structurally sound, and we've used it on hundreds of rammed earth buildings. So Australian Standard 2870, the residential footings code, yes, we have to meet it, but generally we don't step. See, with brickwork, you've got to step down the outside leaf, step up the inside leaf, and have a cavity in between, which makes it quite a complicated footing and quite a complicated detail. We can do it much simpler than that, but I'd need to draw a sketch or do a design. But I mean, we've built rammed earth footings, but concrete footings are absolutely more common. And yes, it's to Australian 2870, but it's a slightly different configuration to the one that you just outlined.
Okay, now Matthew was also wondering, how have you found rammed earth walls on a reactive clay site? Anything to watch out for? I assume the engineer would introduce more articulation joints to counter this. Yeah,
well, that's exactly right. You've got the answer there. Articulation joints. If you look behind me, that line vertically behind me is an articulation joint. So this house, even though it's built on sand, has got articulation joints. Now you get them in rammed earth whether you like them or not, because the formwork is only so long. And so how rammed earth is built is a panel of a certain length is built from bottom to top, full height, then another panel is built along a bit, then other panels and so forth. So you end up with these construction joints between the various panels built on the various days. And those construction joints that we call them are actually articulation joints. So in an earthquake, they allow movement, and in problem clay sites, where there's subsidence and heaving and swelling, they are also the solution to the problem. To do that in fired clay brickwork, in cavity brickwork, is very difficult and very expensive. In rammed earth, you kind of get it anyway, so it's free. So you get it whether you've got a problem clay site or not. But we've built on some terrible problem clay sites, and with great success, and alongside buildings that have had terrible cracking problems, we've had none in a state where all the subsoil was bad. So we're very confident on the problem clay sites, yes.
Cool. I have a question from Andrew. He would like to know if anyone's had experience with bitumen stabilisation of earth.
Do you like to speak, Lance?
It was done in Mildura to stabilise mud bricks. Bitumen emulsion, so it is a water-based emulsion from what I recall, but no, haven't had any other experience other than knowledge of that.
Yeah, if I could add, that Mildura is that same Chris Howe who had a very big mud brickworks at Springfield, which is 8 kilometres out of Adelaide. He moved to Mildura. He uses bitumen stabilisation and it works very well. And most of the Adobe bricks in USA are made with that because their standard requires the brick to be able to be submerged underwater for something like 24 hours, which the bitumen allows it to meet that. We can meet that without bitumen. Rammed earth has been built with bitumen stabilisation, but I personally haven't done it, and I wouldn't really promote it, probably because bitumen's got some sort of health issues.
It also affects the colour. I think one of the attractions of a rammed earth home is the beauty of colour, and you start putting bitumen emulsion in and they don't go black, but they, by jolly, they go a very dark brown.
Okay. I have a question from Karen who would like to know, can you build the whole house walls in rammed earth? How do you do the airflow? Does this mean that you don't need framework or anything else than just the wall?
Generally, the rammed earth would be built in panels. For example, in this house that I'm in, there's the wall finishes, and then there's a door at the end that you can see there. So the design would be done. We would do a design and we would show all the external and internal doors, all the external windows, and then on the external wall, for example, between a window and a door, there might be a solid length of 3 metre rammed earth wall, and it might be, let's say, 2.7 metres high. So we would build that as a rammed earth panel, and then we would go somewhere around the house and then we'd build another panel. And in the end, there would be this thing that looks a bit like Stonehenge, and then the roof would be framed up, and then doors and windows would be put into all those openings. So all the windows would be installed and the doors would be installed after the rammed earth walls are finished and after the roof is on. But the openings would be made as we build. In other words, the openings would be gaps between the rammed earth panels. And windows would typically have rammed earth underneath them and over the top of them and to the left of the window and to the right of the window. Doors would generally, well, obviously they don't have any rammed earth underneath them. They would just have a panel of rammed earth over the top.
Okay. Now, Karen also wanted to know, how do you do a rammed earth slab?
Rammed earth slabs are fairly common and they're not very popular. They generally cost more than regular concrete. We've only done them in areas where concrete was either unavailable or very expensive. So it's the same mix, the same rammed earth mix, but it's spread out and compacted with different equipment, different tools, such as vibrating rollers and plate compactors and things like that. The difficulty is getting them dead level, and the difficulty is getting the heights exactly the same all over the floor. That's a difficult problem. Having said that, in Europe, they're quite common, but they're super expensive there, so they're not very common here.
Certainly earth floors are a little bit common in Australia, and sometimes they're a poured earth floor or a lightly rammed earth floor. I'd call them a tampered floor rather than rammed earth in the same sense. And quite often building code requirements may mean that they're laid over the top of a rough poured concrete slab, just purely to comply with other aspects of the building code. But if you like, a rammed earth floor could go over the top of a concrete slab if that was the effect, look, feel that you required. But unfortunately, some of the building code stuff gets in the way of a good time. So
well, we have done that. In fact, the Kakadu Visitor Information Centre has exactly that. It has a large flat concrete raft slab as a floor, and on top of that we did a fairly thin layer of rammed earth over the top to increase the visitor experience. And I mean, it can have not hundreds of visitors in a day walking over that, and has had for years, and it's a very successful floor. It was done not for structural reasons. It was done so that the people were walking on a rammed earth floor in a visitor information to a famous national park.
Yeah. Okay, Karen also wanted to know, what about earth core in a rammed earth home? Also, where do you put all your electrical running cables?
What was the first word? Earth core?
Earth core in a rammed earth home.
I'm not sure what's meant by earth core, but electricity would typically be run in the walls. There would be a wall box on the face of the wall, and it would have a conduit, and the conduit would go back to the centre of the wall and then down into the foundation or up into the roof space. Plumbing can be run the same way. Sometimes plumbing is run in oversized conduits so that pipes can be replaced. But with electrical, the house is fully conduited, and the wires are run after the completion of the rammed earth walls, and generally after the roof framing, but before the ceilings go in and before the roof cover goes on.
Okay, thanks, Stephen. Andrew has said Bob Rich from Healesville was pushing poured earth for a while. Can you use the same moulds?
I just showed a PowerPoint on a rammed earth wall there. There's a conduit behind that that goes up, and the wiring runs around in the roof space. Sorry, I know Rob Rich, and he was using poured earth. We tried poured earth, and we didn't really like it. The water cement ratio goes all wrong, and therefore it needs much more cement, and the strength was not as high, the durability was not as good. The layering effect, which you can see commonly in rammed earth walls behind both myself and behind Lance, you lost that layering effect, so you lost some of the attractiveness. And in our experience, the cost didn't really come down much. You might think that pouring is easier than tamping, but you've got to remember that with rammed earth, it's quite a damp mix, so you lift it in front-end loaders or conveyor belts. But poured earth is a liquid mix, so you could pump it like concrete. Well, pumping is very expensive for houses, and to pump it for walls where you'd probably have to form up the whole house at once to make the pump viable, so it's not there for too many days, and the formwork cost would then be over the top. With rammed earth, you've got a smallish amount of formwork where you build one wall, then you build another wall repeatedly. You don't form up the whole house at once. So we found poured earth fairly unsuccessful, and I understand there were some contractors doing it in New South Wales, or was it Victoria, I forget, but they don't do it anymore. I'm not really too sure why.
Okay, I'll just
certainly I would think too, your formwork would have to be stiffer, stronger with poured earth. In rammed earth, you're ramming in layers. Effectively, the lower layer is set before you construct the next layer. With poured earth, you have liquid of multiple numbers of tons pushing against that formwork right from the start until it dries and sets. So I think there would be some considerations there that you would need to take on board as well.
Yeah, that's absolutely true. with rammed earth, we've done it where you might build a 6 metre high wall, but if you run out of formwork, you just take some off the bottom and move it up the top. In fact, we used to leapfrog forms in the early days where you'd build a wall, ram it 600 millimetres high, then put more forms on up to 1200, ram it up to 1200, then take the bottom forms off and leapfrog them up to the 1200 to 1800 mark, and then progressively leapfrog the walls up the wall. So you could, the bottom of the wall was exposed because, as Lance said, there's no force. Well, it's dry at the bottom, it's load bearing, it's strong, not dry, strong. Whereas with liquid, with concrete, if you took anything off the bottom, you'd have a disaster on your hand. You've got the full hydrostatic pressure of the full height of the wall, which is how concrete works, and it's very different, and it makes it costly.
Okay, well, we are at 8 o'clock now, so I might wrap things up there. I do note that we have a couple of other questions, but the questions will be saved, and I can ask those to Lance and Stephen via email and get back to you about them. So yes, thanks very much everyone for jumping in, and thank you so much to Stephen and Lance for coming along and providing the information and answering questions, and thank you very much everyone.